Welcome to the Picture Language Seminar. This is probably our last talk for the semester, and it's a great pleasure that we have Zhengwei Lu. He needs really no introduction because he's been here before, but we're very interested to hear about his new way to look at computational complexities. So Zhengwei, we look forward to your talk.
Thank you, Arthur. Thank you for the introduction, and it's very exciting to present this new result on the computational complexity. Well, we have been considering this problem for a couple of years since we discovered the kernel language. We found a topological way to understand tensor networks. And it seems that we should be able to understand those complexity theory also in a topological way. But until recently, we get a better understanding how far we can reach this computational complexity. In particular, we want to understand the complexity in the quantum theory and the complexity in the classical theory, like how far we can extend the computational power by classical computer to reach the quantum computing. And this is kind of the central problem, like when we really have quantum advantage in computation, when we can simulate the quantum system by classical computer. So we know that this subject quantum information is an interdisciplinary subject. It involves multiple backgrounds, in particular mathematics, physics, and computer science. And in this talk, I will talk about three different perspectives. And in particular, how do we learn new ideas from mathematics that can better represent the physics concepts and then enhance the computational power. So first, I will review the background on the quantum computing and classical computing and see how they beat each other. And secondly, I will talk about the mathematical language, how do we design a more efficient language in mathematics to understand the concepts, the physics concepts, and then how do we design good algorithms to understand the computational complexity, and what is the essential difficulty to do classical simulation to quantum system. And by the end, we'll present some examples to illustrate ideas and some brand new examples, and also give some summary and outlook. Now let's go to the background part. So we know that classical computer is reaching the limit imposed by Moore's law recently. Because our computer is very powerful, and supercomputer is even better, but we are really reaching the limit. It seems that we have a technology bound, and we cannot do further, like double the computational power every year. That's just not possible. Because once we go to the small size, we will go to the quantum world, and essentially we need to understand the quantum physics much better. And this phenomenon has been considered by Ani and Feynman in the early days, in 1980s, since we know the problems in quantum physics are usually much more complicated, in particular in multi-body systems. And then to simulate those problems by classical computer is really hard. So we want to simulate those problems by quantum system or by quantum computers. So that's the original idea. And then how to set up such a computer, that's the question. And how to find the interesting algorithm that really beats classical computers, that's another question. So the first remarkable result was given by Peter Shaw for his factorization algorithm that really has somehow speeding up or exponential speed up comparing to all known algorithms on this problem. So that's the very exciting point. And but still, to really reach this algorithm, it's very difficult since we are living in a noisy world, and in particular now for all the quantum system, they have big noise caused by various reasons. So it's called the least square error proposed by Pascal. But still, even though we have this noise, we are trying to understand whether we have experimental demonstration of some algorithms with quantum advantage, like some random circuits, and to produce states that's hard to simulate by a classical computer. So there are such kind of experimental results, quantum like random circuits, Boson samplings, and the recent work of IBM on some algorithms. But on the other hand, several groups are trying to beat those experimental results by classical computer through improving the algorithms in different ways and also using high performance classical computers. So it's still not clear when we can reach quantum advantage in a substantial way and when we can have like meaningful algorithm like Shor's algorithm that cannot be simulated by classical computer. So we do need to understand how far we can use the classical computer to understand the quantum system, what's the limit there. And on the other hand, how to get out of the limit and design meaningful algorithms. So this is kind of central theme. And before in classical simulation process, there are two remarkable work. One is about the Clifford circuits. And it says that such a family of circuits can be simulated classically, even though it can involve like large entanglement and many interesting gates. And in particular, those gates are widely used in design of quantum error correcting codes, like stabilizer codes. And the Clifford gates are usually well performed for like surface code or Tori code. And another one is called the match gate circuits. And this go back to the early study on the fermionic system, like the CI algebra for framework fermis. And some Yang-Baxter equations can be used to do fast commutations to compute the partition function. And in particular, the quantum circuits given by generated by match gates can be classical simulated by computing the Pfaffian matrix, which we know that has a polynomial algorithm. And this is done by the remarkable work of Valiant and many others. So those two are so far the best known families of quantum circuits that can be simulated classically in polynomial spacetime. Well, another powerful method is based on the entanglement. Like if we have a tensor network and we can cut that into small pieces, and once the cutting edge has small number of boundary indices, say k indices, then the vector space is 2 to the k dimension. And if this dimension is still small, say k is bounded by 30, that's beyond the power of supercomputers, behind the power of supercomputers, and then we can still simulate that part. So then we can cut the very complicated tensor network into small pieces and compute each part, and then combine them together. So those are the three major techniques to do classical simulations. Well, actually, recently there are quite different approaches to study like metric product states or projected entanglement pairs, like PEPs, using such kind of ideas to have classical simulation and to understand which kind of quantum states is easy to simulate and which is hard to simulate. Well, the more interesting thing is, even though Cliffords and the match gates are classically simulable efficiently, and they generate the universal gate set, somehow we can present whatever we want in a very efficient way by this hybrid situation, like hybrid circuits or hybrid tensor networks. So we want to understand both. But the previous algorithm for Clifford and match gates are quite different. Clifford is based on kind of symplectic transformation, and match gate is based on this Pfaffian calculation. There's quite different areas and for quite different physics motivations. And it's hard to combine both. So it's not clear how to, even though they give the universal gate set, it's hard to know how to find the better algorithm for both. And somehow we cannot expect to simulate all possible circuits in polynomial time because that involves NP-complete problems, and unless P equals to NP. Well, so somehow the best case people would expect is to have some Clifford gates plus some small number of magic gates, or the other way around. And usually people study Clifford plus some other gates like the T gate or some general phase gate, and consider the phase gate as the resource or magic gate. And the reason is that the Clifford gates can be implemented as the logical gates for various quantum error correction codes. And then we can think about how to implement other logical gates like T gates by different methods. So, and for the magic gates plus something else, that's rarely studied, but it goes back to earlier. It's not inspired by quantum computing, but inspired by some other problems like graph problems, like perfect matching of graphs. If it's planar graph, then it's easy. If it's non-planar graph, it's hard. And also related to early work, very early work on diamond models in statistical physics. So that really has a different direction. So we really want to have a unified classical simulation scheme so that both Clifford circuits and match gate circuits can be simulated classically. There's one algorithm for both. And so that we can extend methods to a more general situation and to see what's the limits for classical simulation. So this is the central challenge. Now, in recent two papers, just posted this Monday, May 12th, 2025. And one is joined with Yunmin Kang, Chen Zhao, Jun Gao, and Songwan Choi on the 2D kernel language. It provides a unifying framework for Clifford's match case and beyond. And second paper is joined with Zixuan Feng, Fan Lu, and Ningfeng Wang on QL classical simulation, also unified in Clifford match case and entanglements. And in both papers, we develop a unified classical simulation framework of quantum circuits and test networks based on the previous study of the QL language, that's a three-dimensional picture language, and the recent work that's joined with Arthur Jeffrey and Alex Wozniakowski, and the recent work called AutoFold topological quantum field theory, which I presented in the two early talks. And this AutoFold TQFT is joint work with Sean Ming, Yilong Wang, Jinsong Wu. So essentially, we extend the QL language to more general three manifolds that has more computational power. And that's actually original motivation for us to study this kind of TQFT. And then we go backwards, just using those new ideas in TQFT and to enhance the understanding of QL language, and then study those classical simulation. And in the first paper, we talk more about the presentations of tensor networks using the QL language. Like somehow, since the Clifford and the match case together are universal, so we can represent all kinds of tensor network using those Clifford and the match case. So just all tractable networks from factories, or everything we found interesting are there, and then we can find this hybrid Clifford match case, match complexities. In particular, this can be used to understand all kind of universal set of quantum circuits, so all interesting circuits are there. And then we can use that to understand the various matrix product states, also in mixed favor, and involved in the Clifford and match gates, and which we know that are classical simulable. And in particular, we extend the idea of match gate to functional match gates and under the planar composition, and showing that's also classical simulable. And in this paper, we talk about how to present those tensor networks by QL language in a favorable way. And to deal with that in a more better pictorial representation, in particular for match gate, we do need a planar condition. So we project everything onto the plane. And once we see the kind of legs or edge in tensor network be projected onto the plane, that's a swapping gate. But we have a planar presentation of the swapping gate, so that can be that. And in the second work, we propose a unified algorithms to classically simulate the quantum circuits on tensor network. So based on those presentations, we can also design algorithms for classical simulation. And then we count the computational complexity in space and time. And we achieve polynomial complexity for both Clifford circuits and match gate circuits. So that's the very exciting point. We do beat this central challenge in this recent work. So that's why we build up this new talk to explain this very exciting work. And now this resolves the central challenge, and also actually we now understand more, since this algorithm is designed by a new complexity that's topological. And that's just as we expected at the beginning, but now we really understand what's going on in this topological complexity. And what is the essential source of the computational difficulty? Like the magic, what's the magic in this work? And that's captured by the magic hole. Later we will see what's the meaning of magic hole. And then we can summarize the result in this picture. Like in general, we can write down those tensor network by pictures, and it may involve many magic codes. So in principle, it can be exponentially difficult. But sometimes we can compute that in polynomial time, in particular when the number of magic code is logarithm. Just like previous case, once the magic resource is logarithm, then we can expand every single term into 2 terms. And then we can solve that in polynomial time. And for the Clifford and matrix, these 2 remarkable circuits, family of circuits, the number of magic codes is 0. That means in this series, both Clifford circuits and matrix circuits are free. That's the really fascinating part. And then you may wonder, okay, then what's the major difficulty in this computation if both Cliffords and matrices are easy? And there must be something difficult when we mix them. So how do we understand this difficulty? So now we need to use this new idea in the topological quantum field theory, the 3-dimensional picture language. And in particular, the QAnon language is a 2+1 topological quantum field theory. So TQFT essentially is saying that we have those manifolds and with boundary, and the boundary can be considered as an input and output. And the manifold called cobordisms with input and output can be used to simulate linear transformations. And if the boundary is disjunct union, then the vector space becomes tensor product. So in the QAnon language, we are essentially using those 3 manifolds to simulate multi-qubit transformations. And then in the output theory, on the boundary of the 3 manifolds, those are surfaces, we will have additional line decorations like braids and many other interesting decorations. And those will enhance the power of presentations or efficiency of presentation of physics concepts, and also with additional computational power. So we will use those diagrams, and in the box, it's just 3 manifolds without decorations. So this has 2 different kind of favors. Now, in the QAnon language, we can provide a unified framework to present this hybrid Clifford and match gate tensor network. And the very exciting part is the following. The match gate lives on the boundary surface. The match gate lives on the boundary surface of the 3 manifolds. And the Clifford gates are given by those braids. The braids are essentially can move in the bulk of 3 manifolds. And this has a very natural understanding in the TQFT literature. Somehow the match gate are coming from the previous study of Ising model, the free fermions. Now on this boundary theory, you can think about that as some data about the Ising CFT on the boundary. And in the bulk, this Clifford are given by those braids. And those braids are essentially the knotting invariance in 3 manifolds in Wheaton's Chen-Simon theory. But here we take a special level. So essentially we are using the computational power. The bulk is the Chen-Simon theory and the boundary is Ising CFT, but in a combinatorial way. And the bulk computation tells us whatever we know about Cliffords. And the boundary computation tells us whatever we know about match gates. And another significance is these 2 computations are independent, are parallel. So you can simplify the bulk computation parallel to the computation of boundary. That's why we can do both together. We can unify the advantage of both. Then what's the remaining difficulty? After we simplify everything on the boundary and everything in the bulk, the major difficulty is if there are some decorations moving globally around the hole, we cannot simplify that in an easy way. So neither the hole nor the local crossings are difficult. But this global topological entanglement, like how stringnets moving around the manifolds, is complicated. That's the major difficulty. So that's the lesson we learned from this new topological complexity. This essential topological phenomenon will tell us the quantum advantage. And somehow we have seen those kind of usage in quantum computing, like when we design Tauri code and many other interesting quantum error correcting codes based on topological orders. Essentially, the useful logical information are coming from those kind of global phenomena, those long-range entanglements. And we do believe those long-range entanglements will give us quantum advantage. And here is a complexity theory to describe or to quantify such kind of long-range entanglement, to tell us what is really the quantum advantage and what's really hard to use classical simulate.
Maybe you'll go into detail later, but it's the number of magic poles analogous to the cubic case, a number of magic gates.
Magic gates here, like for magic gates, just it doesn't count. For Clifford gates, we will see magic gates is still not the main issue. Like magic gates, number of magic gates is not the difficulty for classical simulation. So what's difficult? When the magic gates moving around the hole, that's difficult. So if the magic gate that do not move around the hole, if they just manipulate locally, that's not difficult.
What is the hole?
Yeah, and then we will see what is the hole. Yeah, it's like the plaquette in the tensor network. So this the place that to better describe the ideas, we have to use the QAnon language. We have to take the ideas from TQFT. And that also shows the advantage of this QAnon language comparing to the previous tensor network language. It actually takes a while for us to understand what is the essential advantage of the QAnon language. We see some difference, and we see this has some conceptual way to understanding various concepts in quantum information. But now we really see the essential advantage, the power of this diagrammatic or picture language in quantum information. And in particular, now this really unifies the physics concepts in a very natural way. Now we go to the more mathematical part first to see what's the meaning of those concepts. And then go to the physics part. How do we use the mathematical concepts to understand the physics mathematical language to understand physics concepts? And then we see how do we understand the computational complexity, why this help us to have very powerful classical simulation, and what's the major difficulty, or where is the quantum advantage? So to study QAnon language, now using autofollow theory, actually we have a better approach. This should be accessible even to undergraduate students. You don't even need to know very much about math, physics, or computer science. Only one thing you need to start with is the following. You take a sphere as a boundary, two-dimensional sphere as a boundary of the three-dimensional ball. And on the sphere, you have decoration of closed circles. And then you define a partition function. The value is square root of 2 to the number of circles. That's it. That's everything you start with. The square root of 2 to the number of circles. And then first, you can easily check that this partition function is invariant on these moves. The 4 diagrams with 6 boundary points actually has a relation. And this is actually called the third Jones-Wendell idempotent is not zero, and which is 0. And this is 0 for representation theory of SU2 at level 2. That's how it's related to the previous study in quantum theory. And so that means if you look at diagram with 2 boundary points, with 4 boundary points, you only have 2 vertical lines or 2 horizontal lines. So that gives you a 2-dimensional vector space if you take linear span. If you look at diagram with 6 boundary points, you get 4-dimensional vector space. And if you continue, if you have 2 n number of points, then you have 2 to the n-1 per dimension. So this gives us a hint. We should use them to study the qubit system. And then, what do we learn more from the TQFT, the 3D TQFT? Yeah. From this partition function on the 3 disk with decorations on the boundary sphere, there is a unique extension to arbitrary 3 manifold with decorated boundary surface. There is a unique extension, and such that in this extension we have the following 4 moves. The first one is just saying, okay, we have the decoration for the unit disk, and the value is just square root to the number of circles. And the second one is resolution of identity. You just consider this as an identity map and the vertical composition, and the right side is just decompose that into the sum of bases and new bases. This resolution of identity. And the rest relations are actually the higher code dimension resolution of identities in the higher algebras. So that's the algebraic meaning. And topologically, that also has an explicit meaning. This one means if you take the neighborhood of a point, you can remove that. And this is neighborhood of, oh, sorry, let me go backward. This is neighborhood of point. You can remove that. The white part color is black. And this is neighborhood of a line. You can remove that by this relation. Neighborhood of disk, you can remove that. And neighborhood of ball, you can remove that. So then for any three manifold, you can take a triangulation and remove neighborhoods by that. And then you get a state sum formula to compute this. So this gives you a complete set of relations to compute those decorated three manifolds. So that's how we obtain the partition function. And then by some mathematical computation, we essentially need to show those relations are consistent. So that means the computations are independent of triangulations. And this go back to some standard tricks of our knowledge in QFT. Now, once we have that, then we have those computational tools. And one thing I want to emphasize is this relation. This part has a linear sum. This is the part that causes exponential complexity. So when we do the triangulation, the other three relations are fine. We don't have linear sum at all. But this one, if you count the number of those two cells, you have 2 to the number terms in this state sum. So that's the exponential. So that's the relation we don't really want to use frequently. And that's actually the part when we have low entanglement. That means we have small number of boundary points, and then this vector space. The dimension of this vector space is small. So if that's small enough, then we can still compute that. But in general, we cannot expect that. So that's the major problem. So we have to find new ways to overcome this problem. Now, first, after we have this TQFT theory, how do we understand tensor network? It's quite natural. Take a tensor network. You have the boundary spins or boundary indices, and then in TQFT, you don't have those boundary disks. And the shape are just the same. Just throw up the skeleton into a three manifold, just taking its neighborhood. That's all you need to look at the three manifold. And then on the boundary surface, it becomes more interesting. Since here is a bullet in tensor network. Usually we take a label for some abstract tensors. Now here we put decoration of strings on the boundary surface. And those decorated strings are much more useful to understand the algebraic relations in tensor network, and also various physics concepts that's using those decorated strings. So that's the essential advantage to use Qt language to study tensor network and quantum circuits. And another interesting thing is if we look at three manifolds from tensor network, those are actually called handle bodies, just neighborhood of one skeleton. But the general three manifold could be neighborhood of two skeletons, like torus across a small interval, or some other things. And those are actually very, very useful, like in the design of quantum aircraft codes. So this language has some additional power to express like various concepts. But now in this talk, we will mainly focus on this kind of handle body three manifolds coming from tensor network. Now, to get a simpler case, just form a single qubit. That will be the one valid vertex with one boundary spin. And then in the Qt language or the TQFT, we have one boundary disk. And as we mentioned, if it has 4 boundary points, then it's two-dimensional. So we use that vector space to study the single qubit space. And the diagram is just a linear sum of its vertical strings or horizontal strings. That's the basis. And to get the orthogonal basis, we just take this linear sum to get the orthogonal basis for the presentation. And now we represent this new term orthogonal to that one by this wire, the red wire. And there's another thing we learned from knot theory, is the Kaufman bracket. It's previously designed a linear sum of these two terms, but now we define it in this way. This is a Bredian. It satisfies all the properties you would expect, like the Yang-Baxter equations. So you can move the strings freely based on this Bredian. That's what we learned from knot theory. And the choice of phase is just to ensure that when you rotate this by 90 degree, you go from this one to from positive gradient to negative gradient.
What does each black line physically mean? Does it mean am I around a node?
Well, first, in the mathematical theory, it's just a line. And when we simulate different physics framework, the line will have different meanings. Then later we will see CR algebra, then that will be around a line. But if you see the other like gradients, it won't be like that. It's different for different simulation, we have different meanings for that. Yeah, and actually in John's paper with Arthur on this picture language, we try to explain that just for one mathematical framework, we can simulate different concepts. And then from different physics framework, we can go back, enrich this mathematical framework. And then we go back and forth. And this will lead us to connections of various areas. And actually, that's how we go from Python language to TKFT and then backwards and find something very interesting. And how this could be used to unify Clifford and match gates, those far away things. Since we are really using common diagram to understand different things, but in a more natural way. Now, once we have those wires, we can consider these wires as a pair of Majorana fermions. And later we will see they are really compatible with the usual study of Majorana fermions. And in particular, we have those mathematical relations. Like closed circle is square root of 2, that's the quantum dimension. And if it's a charge with on closed circle, that's 0. It's a parity check condition. And if two charges meet each other, they will cancel. That's certainly like when two Majorana fermion meets, they just cancel. And this relation pairs, when we pair the Majorana fermion, it doesn't matter how we pair them. Just the same. And there's third one, you can have even the braiding. There's a minus sign. And also the charge can move freely on the braids or on the strings up to a phase. And this is the phase for the rotation of this Majorana charge. The two pair rotation will give you a phase -1. So that's a fermion. So we can just derive all the relations from the previous setup, just one by one. But somehow we know those relations in advance. Now we just give a new setup from the very beginning. And also, in general, to understand the phase gate for arbitrary angle, we write this crossing of arbitrary angle as this linear sum. You can consider this is 0, this is 1. And after normalization, we are rotating, we fix 0 and rotate 1 by an angle. And in particular, if the angle is chosen as 4 special parameters, then we have identity and kind of polyword and the gradients. And we consider those diagrams as the Clifford diagram. Later we will see why this is a natural way to think about it. Because somehow those are easier to understand. Like with low complexity, in complexity theory, those have low topological complexity compared to the crossing. So we make the 4 parameters to be special. Now those crossings are very nice. They do satisfy the Yang-Baxter equations, even though they have parameters. That's the dynamic Yang-Baxter equation. And the Yang-Baxter equation is the last one, but to understand this in topological way, we also need other randomized moves, like move 1, 2, 3. And that's those relations. And we do have such relations. So now we can understand the crossings just in topological way, how we move crossing, moving around by those randomized moves. So this essentially tells us how do we reduce the number of crossings just by those local moves. So those are the local relation we can use. Now, what is really special in this Q language is the 2 relations. The first one is that when we change the gradient from positive to negative, we get a pair of charge. And we know the charge can move freely up to a phase. So the charge will have lowest computational complexity, and then the braid. And it's really crucial that we can change all of the gradient, since in general to compute a knot invariant is also exponentially difficult. So to do classical simulation efficiently, we have to involve those kind of efficient algorithm to evaluate knot. And this helps us to untie like links into several layers of unknowns using this single relation. So that's one crucial part. Another crucial relation we know before is this stringiness relation. If we have a hole surrounded by a string, we can remove that. And at that point, this is the only relation we know how to change the shape of the three manifold without exponential cost. So this gives us a hope to have speed up in classical simulation. But all those relations are far from enough. So that's why we see some hints at the point, but we get stuck. Just because somehow we have enough local relations, but for the relations of manifolds, that's the only one we know at the point, and that is not enough. So now let's see how do we use those physics concepts to understand mathematical language to understand physics concepts. The first one is the charge is really like Majorana Fermis. So if we put those lines vertically and consider this as an algebra, and that's actually the CI algebra, and the single charge will be just the generators of the CI algebra, and that's the Majorana Fermi. And when we move the first line just an unsealing line. So this is first and the second for the fermionic theory. And the single charge is always paired by another one on this left wall. And then for CI/CJ, for the anti-commutation relation, it's essentially given by the braided relation. In the step, when we move that, you have a crossing of the red line. And when you untwist the crossing, you get a minus sign. So you just derive the relation in another way. But this is exactly the CI algebra and the Majorana Fermi algebra. And then from the Majorana Fermi, we can, that's actually CI algebra, we can embed that into a Qt language. And actually at the beginning, we read this two-stream model. We first use this algebra, the CI algebra, to understand the multi-qubit transformation. And then we extend that to the four-stream model of the Qt language. And the embedding map is the following. We just embed the strings in those kind of cylinders. And around the cylinder, from one to the next one, we have these cups connecting them. So essentially, in every cylinder, we just have two strings. So this is the embedding map. And this embedding map just exactly from the CI algebra to the tensor product of 2x2 matrices. And that's the Jordan-Wegener transformation. So this is a very natural embedding map. And then for this Jordan-Wegener transformation, if in the CI algebra, we know if we take all the generating unitary, those crossings, and those will give you the free Fermi algebra unitary group. And after we embed that, that's actually the match gate group. So that tells us why the match gate can be simulated classically, because they're just free Fermi theory. And also when we multiply match gate, you will see on the right side, we will multiply those two pictures together. This part will have a hole, but the hole will always be surrounded by those cap and caps, surrounded by the closed string. So that means we can cancel this hole by string genus relation. So by this embedding map, the multiplication of match gates is just the multiplication in the CI algebra. So that means match gate essentially has no holes in the computation.
C3 square equals to C6.
No. C3 means on the third line, we have the generator C. And C6 means on the sixth line, we have the generator C. So the number is the position. And the group generated by those unitary crossing are just match gates. And we know that for match gates, they are actually corresponding to the Qt diagrams without holes. So the three manifold is just a ball with some bounded disks. And then we can prove this general theory. There's a tensor network is a planar match gate tensor network. If and only if it can be represented by Qt language without holes. It's an if and only if condition. And for the qubit system, each bounded disk will have 4 points for single qubits. Yeah, and we can write down generators like for the single qubits, 4 bounded points for match gates. And for the single qubit gate, just like that, we have the lines on the boundary to kill the hole. And those are generally W state or the match state. They are generators of match gates. So essentially, just if there's no hole, that's match gates. If and only if. And the other thing, well, in addition, just if you have planar graph of tensor networks, then you can always kill the plaquette using those purple lines. So essentially no holes in the computation. But for non-planar graph, that's difficult. And indeed, if we do the perfect matching problem, that is a NP-complete problem. So we cannot expect to simulate that efficiently. The planar condition is important for match gates. Now for Clifford gates, So what's that? So first, the polywords by Kittel map is just a kind of like a cylinder with 4 lines, and we put a pair of charge on the lines, and that gives you poly XYZ depending on the choice of pairs. And then the Clifford gates are just those unit pairs that preserves those poly group generated by polywords. And then we can write down the generators of the Clifford group of Clifford tensor networks with those polys and with this S gate and Hadamard gate and the copy tensor and some single qubits. So those are generators of Clifford tensors. And similarly, in similar principle, we can prove that a tensor network, now we don't need 2D condition. So tensor network is Clifford if and only if those in the QAnon language it's a 3 manifolds with decorations, but the decoration is just grid with charge, no parameters on the crossings. So that's the Clifford. So in this case, the results like a magic T will be the crossing. So it's kind of that the story is if we study everything based on Clifford, if we consider Clifford to be easy, then the parameterized crossing will be hard. That's the magic. And if we consider match gate to be easy, the whole will be hard. That calls the non-planar condition. So that's kind of 2 different flavors. So the first 2, Clifford, the last 2, match case, and altogether that's universal. So now we want to understand well how to find the efficient classical algorithm that covers both Cliffords and match case. Essentially, we need further computational tools to reduce those complicated diagrams. And essentially computing the value of tensor network, even with boundary spins, is essentially somehow computing those diagrams. And to get better classical simulation, we want to get minimized number of like crossing holes in this simulation. Well, first, after we see this phenomenon, the first question is we need to understand the classical simulation algorithm of Clifford in this framework. Since the previous algorithm, no matter you use symplectic formalisms or using the Gaussian sum formalisms, they look just quite different. And for match gate also, you can use free Fermis or Pfaffins, it's just quite different, or FKT algorithm, it's just quite different. So the question is, how do we re-understand the 2 results by using new algorithms and then unify them, since the previous algorithm could not apply directly? Now, one thing for match gate is following. For match gate, if it's a diagram without holes, then we don't have to compute that using the FKT algorithm, the Pfaffin. We can use those Young-Baxter relations just by splitting the lines using the random math move 1, 2, 3 and reduce that. Eventually, you get scalar in polynomial time. So that can be done. But for Cliffords, how do we evaluate a number? Think about that. If you want to reduce this graph to a number, then essentially you have to be able to kill the hole. But previously, we only have one rule to kill the hole. That's the stringiness. And that should be not enough. And actually, there is a result in ZX calculus. Say we can do all kinds of computations and reduce Clifford to 0 in polynomial time. And if we compare the relations, since in QAnon language, we have all relations that they know in ZX calculus. So all the relations here will be sound and complete. So we should be able to do it in that way. But they have one more relation, it's called complementary. You have one bullet and you look at all the bullet connects with that and you remove the bullet and write down the complete graph on the rest of the vertices. And that relation is a non-local relation. It involves no bounds of like number of vertices in the graph. And that relation is not derived from the other relations in polynomial time. So somehow they have some elementary relation and then they impose those more complicated relations for free. And that will give a polynomial algorithms. And certainly we cannot use a relation like that. So the single stringiness relation is complete to reduce Clifford to scalar, but not enough to do that in polynomial time. even though the relation sounds incomplete, but that's not polynomial. So then we need to understand this in a better way. We need more relation to kill the whole in a more clever way. And also we need to understand what's the major difficulty, new magic in this result theory. So now we go to the next step, to the computational complexity. Okay. As we mentioned, we have those kind of diagrams to have universal setting, and we need to understand the complexity in a topological way. And the essential difficulty is the global phenomenon. Like how do we eliminate the whole? And the single string genus relation is certainly not enough. And the major difficulty is that how those crossing, it's neither that the number of crossing or the number of hole to be difficult, but how this crossing moving around the hole. So this is a major difficulty. And that's what we now call topological speed. So essentially we can understand this in topological way and also for quantum error correcting theory. This is really the qubit in logical qubit. That's why we call it topological speed.
It's the related topological spin or topological twist in modular tensor cavity of 2D topological order 2+1.
It's related to 2D topological orders, yes. But somehow I would say this is certainly much more than that. That part we don't see this kind of computational complexity figure. And but the theory can be used to study topological order. And actually, if we want to understand the topological order for more general quantum symmetry, then the orthogonal theory will work. That's a unified theory to study topological orders. Okay, now how do we understand the topological complexity? Well, first we consider everything is projected on 2D space. And since it's handle body, we can always switch the order of handle body and consider that as a solid torus and project that on 2D space and moving everything at bottom to top. So we just look at top piece. Well, this is not necessary, but to better view those diagrams on the 2D page, let's present everything in 2D. But essentially, the following concepts can be defined intrinsically in the 3D space. But now let's do everything in the 2D space. So first, we have those holes. You have the holes on 2D space, and you have many diagrams moving around that. So you want to understand this very complicated topological entangled diagrams. And one thing we can do is splitting the diagram into different layers. Because the braiding, we can always change the positive, negative braidings. So we can separate diagram in different layers. Unbraid that. And then for the two diagrams, the strings are in two different parts. The charge are considered to be not connected since they have lowest complexity. And for the braiding, the two different layers are in two different components. And for the general crossings or the input-output disk, they are considered to be fully connected. Now, after we simply split the diagram into different layers, and they are surrounded by the holes, the common holes. So essentially, we are looking at a new network. The holes are looking at topological speed, and they are interacting with each other by those layers. In particular, if one layer contains only one hole, then we can simplify that by area law, but subject to topological entanglement entropy, not a usual entanglement entropy. So we can shrink, no matter how complicated the diagram is, we can shrink everything surrounding the hole to this topological speed picture, to the two layer. The reason is very simple, because this vector space in TQFT is two-dimensional. And this is a two-dimensional vector space. Everything reduced to that. So that's kind of one global simplification surrounding the hole. But now we need more. So first, how to cancel the hole. One thing is we want to generalize the string genus relation. And there is a very natural idea in string manifold theory that's called surgery move. Like string genus means we can kill the hole by the string surrounding that. And after you split that, then you can move everything from left side to right side. And then you can get back the hole. So that means you can move the strings freely. So here somehow it's not that easy to find where is the hole if you have just a string on the surface. And previously we can say, okay, if we have manifold, then we can consider that we have a string on the boundary of manifold, and then find a disk with that boundary, and then glue that, and then we have another string manifold, so that we can have this kind of string genus relation in more general favor. But that's very complicated, and that doesn't work when the string has this crossing on the boundary. The handle slice does work. Now we will see what's meaning of handle slice. So if we have a string that's in one layer, the orange one, they go around two hosts, G0 and G1. Then you see this only the winding number is just 1. So now we count the winding number by parity. It's odd or even. So we only count the odd ones. And then this layer will give us a relation. You just consider the whole as a kind of topological spin with indices 0 or 1. This gives the relation G0 plus G1 equals 0. That's a constraint. And then we can have this kind of handle slice. If you have a layer with this kind of constraint, and then we pick up those holes, and then whatever on the left side of those holes can be moved through to the other side of the hole. That's kind of the generalization of the string genus relation, but it's really in the favor of handle slice in series theory of string manifolds. And then you can imagine that if you move everything from left to side, then there's nothing to do with the hole. Then you can cancel the hole. So in this way, we can also cancel the hole, but not at the beginning. We cancel the hole at the end. We move everything first, and then we cancel the hole. So in this way, once we have a constraint, then we can cancel one hole. So it's kind of generalization of the string genus relation. It's one odd constraint. We can cancel one hole. And then for the hole, for the remaining hole, after we remove all the holes that's odd, meaning some layer, for some layer, the winding number is odd, we just eliminate that. And eventually, all the holes are even. That means for any layer, it always go around the hole even times. And then for the even holes, we need two different conditions. Like here, we still have the question, if we have even holes, like for the Clifford case, how do we remove them efficiently to have classical simulation of Clifford circuits? So we say that a hole is Clifford if the layer surrounding the hole is just those braided diagrams without parameters on the crossing. So if the hole is just surrounded by a Clifford diagram, it's called a Clifford hole. Otherwise, it's non-Clifford. And if it's even and non-Clifford, then we call it magic. So in next class, we will show the Clifford code can also be eliminated, but the magic code is not. So that is a major difficulty. Now for Clifford hole, the relation is that after we say if G0 and Clifford hole is surrounded by many layers of Cliffords, and those layers will involve many other holes, so G1 to Gm. And then when we remove this hole, we only need to make up one diagram, this double string with crossings surrounding the holes, depending on the topological entangled conditions. And this alpha has only 4 choices. So this crossing is Clifford. It's not a generic crossing. So that means we can remove the Clifford hole without increasing complexity. We don't increase non-trivial crossings, but we remove the hole. So eventually what we are left are just those magic holes with those crossing diagrams moving around the magic holes. Then we end up with this picture. So if the number of magic holes is logarithm, then we can remove every single hole into 2 terms. And then we can eliminate all the holes to 2 to the logarithm. And that's still polynomial. And then the rest of the graph will be the match gate graph. And we have the Pfaffin commutation, or Yang-Back relation evaluation. So this part will give us a closed form formula. As 2 to the so many holes, this state sum form. And as we mentioned for Clifford, every hole is Clifford, so everything can be eliminated. So no magic hole. Match gate, no hole at all. So for both cases, there's no magic hole. So those 2 circuits are free in the series. So the essential difficulty is the number of magic hole. But actually, the more conceptual way is that not just the magic hole, but how the crossing moving around the host. That's the really difficult part. Since if we have less number of crossings, then we can do it like for magic, like for T gate, we can simply T gate and sum of another 2 Clifford gates, and then everything becomes Clifford. So we can still do that. So it's essentially not number of hosts, but not number of crossings, but how they move around each other. That's the major difference. And then we can go even further. Well, we have those magic hosts. How do we eliminate magic hosts? We want some more powerful relations to design better algorithms. Like for topological space, if we have 2 topological spaces meeting each other, then this is the fourth string. Then we can move one crossing to the other side, and then add up the angle. And then this will be 2 strings go around the hole, and then we can kill that using string genus relation. So that means when 2 topological spaces meet each other, then we can cancel one of them. And this topological space is one kind of magic host. So that's very powerful. So once we have this elimination, then essentially we are having an exponential spinning up for this classical simulation. And this is another relation. If 2 hosts only have 2 lines in the middle, then we can cut them and eliminate the one hole. And the very powerful one is this. So if you have a hole, like magic hole or topological spin, if it's not surrounded by a layer, then you can move that. This is another kind of handle slice relation for magic holes. And very useful. Think about that. You may have one magic hole here and one magic hole there. They are separated by the layer. But then you can move one freely to the other one and you cancel them using the first relation. So this is essentially if the network is not that complicated, then we can cancel those magic holes very efficiently. So that's why the essential complexity is those topological entanglement of this network, or like for different layers surrounding those hosts. That's the major complexity. Now we'll give an example to see how this could work. So this is circuit. The input qubit is like +0, and just by direct plus means double cap, this one, and 0 means 2 small caps. And then you can extend this as large as you want to scale up. And this is a family of quantum circuits in the middle with On widths and On depths and N square Clifford gates and match gates. And the output state has like kind of large entanglement. There's all kind of bad properties if we want to consider this for classical simulation. And then somehow if we want to simulate the measurement of this, then essentially we need to compute the conditional expectation of every single qubit measurement in polynomial time. Then we can simulate the sampling process. And here this small circle means it's just a hole surrounded by a single spin, and the small cross here is just a topological spin. And for local part, each local part, we can rewrite that. Just finally, any 2 holes have 4 strings in the middle. So this is a circuit. That's a 1+1 circuit. And what makes it more interesting is for when we measure the qubits in a Z basis, then this is classical simulable. Namely, the conditional expectation can be computed in polynomial time. So why? So if I have the small cap for the measurement, small caps here, then you can move this cap, just move it around, go to the top. Since this is string genus, you don't see that. You can just move that to top. So essentially, this connection it's not really connected. There's no topological entanglement between them. You can just split the diagrams using the Yang-Baxter relations. So those Yang-Baxter relations are no local move. So in this case, that can be simulated classically efficiently, and it can be done by classical method, like all kinds of local moves, no matter topologically or algebraically. But if we measure them just like top by +0 basis, then this will be very subtle. Then you will have the cap here, and then this crossing will be in the middle of this layer. Then you cannot move the crossing easily. And essentially, in that case, you will have like different layers in this direction, and one layer, another layer, like n layers in this direction, and n layer in that direction, and then you have those crossing inside. But if you look at that carefully, you will see those crossing is inside in those layers, but outside those that layers. And then you can use those free moves. You can move the crossing across in the layers, and then so that all those crossing will cancel with each other. And then still this is classical simulable, but in this case you need the global moves. This cannot be done locally. This local Yang-Back solution or other algebraic method, none of them should work because this is indeed a global move. And the third one, when we measure them in the x basis, then essentially we change the position in the layer, you change the x in the layers. Different measurements give you different kind of layers. And in that case, the crossing will be in the intersection of layers in this direction and that direction. Then we cannot move them at all. And that's hard to simulate. So same circuit, but different kinds of measurement gives three kind of results. One is easy to classical simulate by local moves. Secondly, easy to simulate, but by global moves, not local moves. So that previous method won't work for the second case. Third one is hard to simulate. So now in summary, this Q1 language classical simulation first give us natural presentations of tensor network, and it's universal. And in particular, the Cliffords are essentially the three-dimensional structure captured by manifolds and Brilliance in manifold. And match gates are captured by 2D structure on the boundary. And this gives a topological complexity to describe those kind of topological entanglements of network. And then we design the algorithms and to show what can be exponential, what can be polynomial, and to see where is the quantum advantage coming from. And we define several things. We try to do classical simulation as best as we can. So we need to do crossing reduction by the Yang-Back relation, but it's local reduction, and also genus reduction by the surgeries for Clifford holes, and then some additional magical reduction by those kind of free moves for magical with layers. So essentially, we are applying this Q1 language as a 2+1 topological quantum field theory with space-time boundary, and the efficiency of simulating Cliffords is a generalization of surgery theory. But surgery theory is not enough, since that's only for odd hole elimination. Here we need even hole elimination. That's particularly designed for Cliffords. That's certainly not true for arbitrary TQFT or kind of TQFT of other quantum symmetry. That's just not the case. So we are very lucky to have this relation here. And the other thing is the match case by the 2D moves on the boundary. Okay. So again, the essential exponential difficulty is neither the number of crosses nor the number of holes, but the topological entanglement of the network, how those crosses moving around holes. That's the essential difficulty. So now we have this very nice classical simulation framework and very powerful algorithms. So using that, we can compute many things efficiently by classical computing. This will reduce the cost, like the experimental cost in sampling. Like when we design an algorithm or quantum error correction codes or many other things, several algorithms requires the measurement. And that's highly cost. And then now here, if we have more powerful classical simulation method, then we can simulate the training progress, like the gradient flow and many other things by classical computer. And this is much cheaper. And after we have a circuit, then we run it in the lab. I think that's a better strategy. So in that way, we can take advantage of this classical simulation. And eventually we see where is the essential quantum advantage. In particular, in the next step, we want to understand what is the essential quantum advantage in Shor's algorithm and how far we can classically simulate that Shor's algorithm. And we want to understand this topological complexity for some other frameworks like topological orders or quantum error correction codes or long-range entanglement, which has been studied quite a lot. And now we want to understand this in this new complexity figure. And also started general theory of this tensor network. And actually, this has an additional framework to reduce the number of number of magic holes, similar to the area law. If I have smaller entanglement, then we cut the tensor network and compute every small piece. Here, similar. If the topological tensor network is not that complicated, then we can compute the local piece with respect to topological entanglement. Not just usual entanglement, but topological entanglement. And that can be done as well. Say if you have many layers with only several small number of holes inside, then you can simplify this part first, and then the next part. So that's the topological tensor network. And somehow I think the most exciting part is this algorithm really captured the global phenomena of the quantum circuits. So I think we should go to an era to study the global phenomena of quantum circuits. And it seems that the quantum advantage really comes from those global structures. Thank you.
Yes. Thank you, Zhengwei, for a very beautiful talk. And I'm sure there are a lot of questions or discussion. Let's see. Yes, Alex.
In the topological spin diagram for relation that two of them on the multiply the parameters. I'm curious if you have multiple. They have to be an equal number of chances to be able to
Yes,
interact. Or
that's a very good question. That's why I say this is essentially a 3D language, not 2D. So now, if we have a diagram like this, so how do we simplify that? The answer is following. So even though you see two holes here, but in the 3D space,
Zhengwei, maybe you could remove your share.
yes. Yeah. So even though you see two holes here, but in the 3D space, if you look at it in a different way, you may see one hole. And then let's go back to a single hole, and then you can use that relation. So whether this is one hole, two hole, it actually depends on how you project your graph to the 2D space. So that's the major advantage of the 3D theory behind this. And actually, all those concepts can be defined intrinsically in 3D space. And there, we are able to prove a result saying that the number of magic holes is a 3D concept, not 2D concepts. Just no matter how you eliminate the out holes and the Clifford holes, no matter how you project that in 2D space, there is a linear algebra to describe the process. And the different choice of the holes correspond to change of basis. And the number of magic holes is essentially given by the rank of the matrix. But the change of basis is an invertible linear transformation, and that doesn't change the rank. So this is actually a 3D concept.
So also in the projection, the parameter change based on this projection.
Yes. Then we can change the parameter. We can move this from this side to that side, and then cancel one hole by the string geometry, and then we have another hole left.
So aside from this O log n bound, do you have any other quantitative bounds?
Well, for the last example, actually, the number is not log n. The number of magic hole is still n squared. Yeah, but since we can move the magic hole across in the layer, and then we can still cancel them. So log n is not the necessary bound, but just theoretically, we know once we reduce this to log n or to a small number, then we can compute that. So in practice, there are several other methods to improve this, just similar to the previous study of like magic T-gates in result theory, even though we say logarithm, but there are other methods like polyrank or some low entanglement to reduce the computational complexity. And
So can you use these methods to improve the computational of manifold invariance?
that's a very good question. To compute manifold invariance, actually, first, when people compute manifold invariance, it's usually not polynomial. It's just always exponential. And that's why we say that if we just have nothing invariant in the computation, that's certainly not enough. And we are very lucky to be able to change the crossing. And then for this qubit case, the two relevant not invariant can be computed in polynomial time. The 12 very invariant and the range-taking 12 invariant. Like for example, the 12 very invariant of the manifold is given by the number of the fundamental group of the manifold to the homomorphism from that to Z mod 2 or Z2 theory. And this is essentially solving some linear equation in this field. So this can be done in polynomial time, but these are also known before. So that's why this theory works for classical simulation, essentially because this can be computed in polynomial time. And once we go beyond the theory, like if we simulate this qubit system using like Fibonacci adding, not by this adding type of system, then it won't work. Because computing the braid system for big Fibonacci adding is exponentially difficult. But there's another thing that could be useful. That's my recent work on this construction of 3+1 IZ. And that part is also has a favor like this. Like we can switch the braiding, but not the line braiding, but the surface braiding for free. And so that may produce another powerful picture language is like 3+1.
Is that 3+1? I think you mean something like 3+1 equal to 1 model.
It's not that. It's not that. It's another kind of Egan type of 3+1 theory. Walk one is a general theory. It's designed for modular tensor category, but essentially for line defects. But I'm talking about a 3+1 Egan theory with surface defects.
So it's beyond MTC.
It's certainly beyond MTC. Yeah, but just for computing manifold invariant, it's certainly hard, usually exponential. And this won't be useful for that. And we just have the kind of common playground such that on both sides it's polynomial.
So are there any other questions? Well, if not, let's thank Zhengwei again and look forward to your next visit.
And also, I would like to thank Arthur and also with my students. We are very grateful to the hospitality of Arthur Jeffrey for our visit this time and also for all previous training of my research and many other things in my life. I'm really grateful to Arthur. Thank you.